In this chapter, we will provide you with a bird's-eye overview on the Java technology. Let's start with the chapter outline. We will kick off by presenting a short history of Java. We will discuss its key features and take a look under the hood of the Java technology stack. We will then zoom into the Java language structure and conclude the chapter by reviewing Java data types. It is important to note that this chapter lays the foundation for subsequent chapters, and many of the concepts and ideas presented here will be elaborated further on as we proceed through the course. Sun Microsystems developed the Oak programming language, later renamed into Java, already in 1991. It was meant to be a cross-platform, portable programming language to be used in home appliances such as TVs, VCRs, washing machines, refrigerators, etc. Although this language was not that successful as such, the emergence of the World Wide Web gave it a new boost, and in 1994 the first Java-enabled web browser, Hot Java, was introduced. A year later, Netscape introduced Java support in its famous web browser, Netscape Navigator. The first version of Java, Java 1.0, was introduced in 1995. In 1997, Sun made Java available as open source under the GNU General Public License, GPL. In 2009, Sun was acquired by Oracle, which continues its development. Here you can see an overview of the various important Java releases and their characteristics. In this course, we will make use of the Java SE8 release. Let's now take a look at the key features of Java. First of all, Java is a simple programming language. Its syntax is quite easy to learn and very similar to C or C++. Furthermore, it has lots of built-in facilities and predefined packages which will facilitate the development of software applications. As already mentioned before, Java is platform independent and portable. This is especially handy in today's networked environment, which consists out of different hardware and software platforms. Think about Microsoft, Apple and Unix or Linux platforms, for example. The goal of Java is to implement a write once, run everywhere approach, whereby a Java program can be easily executed across all these platforms. Java is object-oriented. It works with classes and objects. Remember, an object is an instance of a class, or a class is a blueprint description of a set of objects. It basically groups data or properties together with methods or operations. We already briefly discussed the example of the BMI class to calculate the body mass index, but we'll provide more details of this in later chapters. Another key feature of Java is that it is secure. This is especially important in a networked environment. Java has built-in facilities to safeguard access to networked resources and carefully oversee memory allocation. From a performance perspective, Java also supports multithreading, whereby different lines of code can be executed in parallel memory threads. Finally, Java is dynamic by enforcing a strict separation between interface and implementation. In other words, at runtime, it is decided which Java code should be executed. This makes it extremely flexible. Let's now take a look under the hood of the Java technology stack. In what follows, we will discuss bytecode, the Java Runtime Environment, or JRE, Java platforms, and various types of Java applications. Remember, Java implements a write once, run everywhere approach, whereby a Java program can be easily executed on various platforms such as Windows, Mac, Sun Solaris, etc. To successfully accomplish this, Java adopts both the compiler and interpreter approach. In other words, a Java source program, such as bmi.java, which implements our BMI class, remember, will be compiled into bytecode bmi.class, which is a platform-independent intermediate language. During this compilation step, programming errors can be detected. Do you still remember the various types of programming errors from our first chapter? The bytecode will then be parsed by a platform-specific interpreter in order to execute it. An interpreter is an implementation of the Java Virtual Machine, or JVM, which can be thought of as a virtual CPU or a virtual central processing unit. Here you can see the bytecode for our BMI calculator example. Remember, this is platform-independent code. The Java Runtime Environment, or JRE, is the software component. Let me do that again. The Java Runtime Environment, or JRE, is the software environment in which the Java programs run. Its components are the Java Application Programming Interface, or API, the class loader, the Bytecode Verifier, and the Java Virtual Machine, or JVM. Here you can see the outline of the JRE and how the various components interact. Let's get into some more detail. The Java Application Programming Interface, or API, provides you with predefined functionality, offered by means of Java components grouped into libraries. Here you can see some examples. Let's highlight some. The java.awt and javax.swing libraries support the creation of graphical user interfaces, or GUIs. In other words, they allow to create forms, buttons, drop-down boxes, menus, etc. The java.math library implements various mathematical routines such as calculating the average, maximum, minimum, factorial, absolute value, etc. The java.sql library allows to access and work with relational databases. Many of these libraries will be discussed later in this course. Note that as you start getting more proficient with Java, you can also develop your own libraries. The class loader locates and reads the class files needed to execute the program and loads the corresponding bytecodes into memory. Classes are typically assembled into libraries and stored as Java archive or jar files. The class loader consists of three subcomponents. The Bootstrap class loader loads the core Java libraries located in your Java home JRE lib directory. The Extensions class loader loads the classes from the Extensions directory, which is Java home JRE lib ext. Finally, the System class loader loads the code from the location specified in the class_path environment variable, which is defined by the operating system. The Bytecode Verifier checks the validity of the bytecode. It will carefully type check all variables and expressions and ensures no unauthorized access to memory. Remember, one of the key features of Java was its security. The bytecode verifier can be disabled to improve performance. Once the bytecode has been verified, it can be offered to the Java virtual machine. The Java virtual machine can be thought of as an abstract computer capable of executing bytecode on a particular hardware and software platform. The most popular GVM is Hotspot, developed by Oracle. The interpreter is the heart of the GVM and executes the bytecode. The garbage collector cleans up unused memory. The GVM also includes facilities for multithreading and synchronization to improve the execution performance. The JIT compiler is an environment-specific component. It allows to compile the bytecode of frequently executed instructions or hotspots into native platform-specific code so as to speed up the execution. A Java platform or edition consists of a Java runtime environment, GRE, with a specific set of libraries for a specific application environment. Here, you can see an overview of some common Java platforms. The J2SE platform is the core Java platform designed for applications typically running on desktop PCs. The J2EE focuses on business applications. J2ME targets embedded applications such as for mobile phones. Java Card focuses on smart card applications, and JavaFX supports rich internet applications. The most popular type of Java applications are standalone applications, Java Applets, Java Servlets, and Java Beans. Let's get a closer look. A standalone application can run independently on its own. It only needs a GVM to execute. In the upper left corner, you can see a standalone command line application to calculate the BMI. In the lower right corner, you can see an example of a GUI application to calculate the BMI. Obviously, a GUI application is more user-friendly than a command line application. A Java applet is a Java application which is typically embedded in an HTML page. It's run by the client web browser. To ensure security, Java applets will be executed in a confined memory space called a sandbox. Applets are included in an HTML page by using the applet tag. They were originally used for graphics and rich interfaces, but are not that popular anymore. Servlets are part of the J2EE platform, which targets business applications, remember. They run on a Java-enabled application server. They can handle multiple incoming requests, interact with server databases, invoke web services, etc. Finally, Java Beans are reusable software components that can be visually manipulated in a software tool. You can see an example here of NetBeans, which is an Oracle Integrated Development Environment, or IDE, providing support for Java Beans. To the right, you can see various types of graphical components, such as panels, labels, buttons, etc., which can be visually added to the frame using drag and drop. In the next section, we will zoom into the Java language structure. More specifically, we will start with an introductory example and then discuss classes, identifiers, Java keywords, variables, methods, comments, and naming conventions. Let's get started. Here you can see a running example. The Java class BMI calculator allows to calculate the BMI of a person. Remember, the BMI is calculated as the weight divided by the height squared. A couple of things are worth noting here. First of all, Java is a form-free language. In other words, any statement can start at any place of indentation. White spaces, tabs, and new lines can be added wherever desired. To facilitate the readability of your Java code, it is recommended to adopt a consistent formatting style. Another thing worth noting is that every statement ends with a semicolon. A statement can also span multiple lines. The screenshot to the right illustrates the output of this program after invoking it from the command line. Let's now more closely inspect this BMI calculator Java class. A Java class is essentially a code container. A class definition starts with an access modifier, which is public in our case. This specifies where the class can be accessed from. We will discuss this into more detail in a later chapter. The access modifier is followed by the keyword class and the name of the class, which is BMI calculator in our case. A class definition is enclosed within brackets. A Java class has both variables, such as weight, height, and BMI in our example, and methods such as BMI calculator, calculate BMI, and main in our case. The main method is a special method, since it is the entry point of program execution. In other words, when our BMI calculator class is executed, the main method will be executed first. An identifier is the name of a language element, such as the name of a class, variable, or method. Examples in our case are BMI calculator, which is the name of the class, weight, height, and BMI, which are variable names, and main and calculate BMI, which are method names. An identifier cannot begin with a digit and cannot be a reserved keyword, as we will discuss in a moment. Important to note is that Java is case sensitive. In other words, the three BMI identifiers at the bottom here will all be considered as different by Java. Java has 50 predefined keywords, which you can see listed here. These have a special reserved meaning in Java and cannot be used as identifiers. In our BMI example, we use the keywords public, class, static, void, and double. Most of these keywords will be covered in later chapters. Remember, a Java class has both variables and methods. A variable is a name for a memory location that stores a specific value. This value may change during program execution. In our BMI example, we have three variables: weight, height, and BMI. All three are defined using the data type double, which represents a floating point number. Besides variables, a Java class also has methods. A method is a piece of code that performs some specific functionality. In Java, a method definition needs to be enclosed between brackets. In our BMI example, we have three methods: BMI calculator, calculate BMI, and main. Let's have a closer look at the main method. Remember, this is the entry point of program execution. So it is the first method that is executed when our BMI calculator class is run. The main definition starts with public, which is the access modifier specifying from where the method can be called. We will discuss more about this in a later chapter. The keyword static indicates that the method does not need an object. Void means that the method does not return any value, and string args indicates that the method takes an array of strings as its input parameter. The method then continues by defining a BMI calculator object, which is called calculator. This object is assigned a weight of 60 and a height of 1.70. Next, the calculate BMI method is called for this object, which will calculate the BMI and return it as the variable BMI. The latter will then be printed to the screen using the final statement. Don't worry if this seems complicated at this stage. We will extensively explain the meaning of all of this in subsequent chapters. Comments are a very handy feature to improve the readability and facilitate maintenance of your Java code. They are ignored by Java and thus not executed. Java has various ways of defining comments. You can use // to include a comment that runs until the end of the line. Block comments, which span multiple lines, can be defined using / asterisk at the start and * at the end, as you can see illustrated here. The Java doc tool, produced by Oracle, can also be used to produce HTML documentation from Java source code. To facilitate the readability and maintenance of your Java programs, it is highly recommended to adopt a consistent naming convention. Here you can see an example of this. Java classes can be defined using upper camel case, whereby the first letter of each word is capitalized. Java variables and methods can be defined as lower camel case, whereby the first letter is lowercase and the first letters of all following words are capitalized. You can see some good and bad examples of this in the table. In the next section, we will zoom into Java data types. We will start with an overview and then discuss primitive data types, literals, operators, arrays, and typecasting. Java is a strongly typed language. In other words, every variable should be carefully defined before it can be used. A data type specifies how much memory to allocate to a variable, its format, and the operations that can be executed on it. A further distinction can be made between primitive and composite data types. A primitive data type is a basic building block supported by Java. A composite data type is a composition of primitive or non-primitive data types. In our BMI example, we had three variables: weight, height, and BMI. All three are assigned the primitive data type double, which represents a floating point number. Java has 8 built-in primitive data types, as you can see illustrated in this table: byte, short, int, long, float, double, boolean, and char. The table also specifies the minimum and maximum value together with the default value. Important to note here is that Java does not have a built-in string data type. We will discuss how to work with strings in a later chapter. A literal is a value assigned to a variable of a specific type. Here, you can see some examples of this. We assign the literal or value 60 to the variable weight. Note that the equal sign is used as an assignment operator. Another example is where we assign the literal true to the variable overweight, which is of type Boolean. You can also see 3 examples of assigning a literal to the BMI variable. The latter is expressed in scientific notation by using E. We assign the literal B to the variable initial, which is of type char, representing a character. Unicode characters can also be used to define character literals, as you can see for the British pound symbol. Also, escape characters such as backspace, tab, line feeds, etc. can be defined. Operators perform data manipulations on one or more input variables called operands. In what follows, we will discuss arithmetic operators, assignment operators, bitwise operators, logical operators, and relational operators. Arithmetic operators perform the basic mathematical operations, as you can see illustrated in this table, with the addition, subtraction, multiplication, division, and modulo operator. The latter represents the remainder after integer division. In other words, 8 modulo 3 equals 2, since 2 times 3 equals 6, which gives us a remainder of 2. The modulo operator is often used to check whether a number is even or odd. For an even number, %2 or modulo 2 will result in 0, whereas for an odd number, modulo 2 will result in 1. Here you can see the assignment operators listed. An assignment operator assigns a value to a variable. We already discussed the equal sign as an assignment operator. We assign the value 85 to the variable weight. Weight plus equal 2 is a shortcut notation for weight equals weight plus 2, so the result becomes 87. Weight minus equal 2 corresponds to weight equals weight minus 2, so the result becomes 85. Weight star equal 2 is the same as weight equals weight times 2, so the result becomes 170. Weight slash equals 2 and weight percentage equals 2 can be interpreted accordingly. Weight plus plus corresponds to weight equals weight plus 1, and weight minus minus corresponds to weight equals weight minus 1. The latter are very handy shortcut notations, as we will discuss later. Bitwise operators work on bits and perform bit-by-bit operations on the operands. Let's assume we have 3 variables a, b, c, which are of type byte. Remember, the data type byte represents an 8-bit signed integer. The binary representation of 40 is 0010, 1, 000. Since 2 to the power 3 plus 2 to the power 5 equals 40, so we put a 1 in position 3 and 5. The bitwise AND operator puts a 1 bit in the result if both input operands have a 1 bit at a given position and 0 otherwise. The bitwise OR operator puts a 1 bit in the result if one of both input operands has a 1 bit at the given position and 0 otherwise. The bitwise exclusive or XOR operator puts a 1 bit in the result if one of the operands, but not both, has a 1 bit at a given position. The unary bitwise inverse operator changes every 1 bit to 0 and every 0 bit to 1. The signed right shift operator shifts the left operand to the right by the number of bits specified. The left digits of a positive number are then filled with zeros, whereas the left digits of a negative number are filled with ones. This allows to preserve the original sign of the number. The unsigned right shift operator shifts the left operand to the right by the specified number of bits. The left digits are always filled with zeros, regardless of the sign. The left shift operator shifts the left operand to the left by the number of bits indicated. The right digits are then filled with zeros. Since only the right side is filled, it is not possible to fill with ones or zeros to ensure a positive or negative number. Therefore, there is no distinction between a signed left shift and an unsigned left shift. A logical operator is also known as a Boolean or conditional operator. It uses Boolean operands and returns a Boolean result. Consider the following two example Boolean expressions: A, which states 3 is bigger than 2, which is obviously true, and B, which states that 2 is smaller than 1, which is obviously false. The conditional AND operator evaluates to true if both operands are true. In our example, A and B evaluates to false. The conditional OR operator evaluates to true if at least one operand is true. In our example, A or B evaluates to true. The logical XOR operator evaluates to true if one and only one of the operands is true. In our example, A XOR B evaluates to true. The unary NOT operator evaluates to true if the operand is false and vice versa. In our example, NOT A evaluates to false. Here you can see the truth tables for the Boolean operators AND, OR, XOR, and NOT. It lists the outcomes for the various possibilities of the operands. The bitwise AND and OR operators can also be used with Boolean operands. However, there is a difference between the logical and bitwise AND and OR operators. The bitwise operator will always evaluate both operands. The logical AND operator will not evaluate the second operand if the first one evaluates to false, since it then already knows that the outcome will be false anyway. Likewise, the logical OR operator will not evaluate the second operand if the first one evaluates to true, since it then already knows that the outcome will be true anyway. This behavior is referred to as short-circuiting behavior and allows to speed up the performance or handle possible error-prone expressions. Relational operators check the relationship between operands, which are usually numbers. They typically return a Boolean value. Suppose we have three integer variables: A initialized to 4, B initialized to 9, and C initialized to 4. We can now check whether one is strictly greater than, greater or equal than, strictly lesser than, or lesser or equal than the other as illustrated. We can also verify if one operand is equal or not equal to the other as represented in the bottom two rows of the table. An array is a composite variable, holding a fixed amount of values of a specific type, such as int, long, char, etc. The elements of an array can be accessed by means of an index, whereby the first element of an array has index 0. An array is defined by using square brackets. The first two statements here are equivalent and define a variable weight array representing an array of floating point numbers. The array can then be initialized using the new operator as illustrated by the third statement. Weight array equals new float 5. We can now store 5 floating point numbers in the variable weight array. Remember that the first value is stored at index 0 and the final value at index 4. The values stored initially will be the default values, which is 0.0 for float. Here you can see how the array can be populated with floating point numbers. Note that we add the letter F at the end of each number to indicate that they are floating point numbers. Declaring, initializing, and populating an array can also be done more concisely as illustrated by the final statement. Here you can see an example of a Java program using arrays to calculate the BMI for 5 people. It uses 3 arrays: weight array, height array, and BMI array, each containing 5 floating point numbers. We then assign values to the weight array, as you can see at the bottom. We also assign 5 values to the height array and then calculate the values for the BMI array, as you can see illustrated. The latter is then printed to the screen. Again, note that the first value is at index position 0 and the final value at index position 4. This shows the output of our program. Multidimensional arrays are arrays where the elements are arrays themselves. A very popular example of this are matrices. Here you can see a variable, matrix, which represents a matrix with 3 rows and 3 columns. It is declared using 2 double square brackets to indicate that it's an array of arrays. The elements can then be accessed accordingly. What do you think is the element at row 1, column 2 of the matrix variable? Indeed, it's 8. We can also create arrays of unequal sized arrays or jagged arrays. This is illustrated here. The weird matrix variable has 3 elements. The first element is an array with 2 numbers. The second element is an array with 3 numbers, and the third element is an array with only 1 number. Again, the elements can be accessed accordingly. What do you think is the element at row 1, column 1 of the weird matrix variable? Indeed, it's 6. We will conclude this chapter by explaining typecasting. The idea here is to convert a value from a specific type to a variable of another type. First, remember the hierarchy of primitive data types. From high to low precision we have double, float, long, int, short, and byte. A widening conversion, or implicit casting, is when the value of a narrower, or in other words, lower precision data type is converted to a value of a broader or higher precision data type. Obviously, this causes no loss of information. Here you can see an example. We have a variable a, which is defined as an integer first. It is then promoted to a double. To make the casting explicit, we can add double in front of the a, as you can see illustrated here. A narrowing conversion is when a value of a broader or higher precision data type is converted to a value of a narrower or lower precision data type. This will typically involve loss of information. Here you can see an example. We define a floating point variable b and then try to cast it to an integer. This will typically not work and an error will be generated saying, type mismatch, cannot convert from float to int. We have to make the casting explicit by adding int in front of b, as you can see illustrated. Here you can see some examples of type casting. We define a variable int a, which is an integer initialized to 4. The float b variable is a floating point number initialized to 6.82. We then define a variable double x, which is defined as int a cast into a double. Do you think this is a widening or narrowing conversion? Indeed, it's a widening conversion, since double has a higher precision than int. We then define the variable int y, which is obtained as the variable float b cast into integer. Do you think this is a widening or narrowing conversion? Indeed, it's a narrowing conversion, since int has a lower precision than float. To the right, you can see the output of our program. Observe that the narrowing conversion of the float b variable caused the floating point to be dismissed, resulting into the value 6. Here you can see another example of casting. For the first statement, float x equals 3 divided by 9, Java will consider both operands as integer, then apply integer division, which gives 0, and then do the widening conversion to float, yielding a 0 floating point number. For the second statement, float y equals float 3 divided by float 9, Java will first perform the widening conversion for the values 3 and 9, do the floating point division, and assign the result to the floating point variable y. For the third expression, float z equals float 3 divided by 9, Java will first do a widening conversion for the value 3, followed by an implicit widening conversion for the value 9, then perform the floating point division, and assign the value to the floating point variable z. To conclude, in this chapter we started by providing a short overview of the Java history. We then reviewed the key features of Java and took a look under the hood of the Java technology stack. This was followed by an introduction to the Java language structure. The chapter concluded by discussing Java data types.